Alright, so in this video I'm going to be demonstrating a hash cracking tool that I developed in Python that just shows the importance of password length and complexity. So I'm just going to walk through the code real quickly, then just show some real world examples and applications of the tool. So first we'll just look at the libraries we're using. First and foremost we'll use argparse, which we're going to be using for handling command line arguments. The arguments are going to be the hash itself and then the word list that we want to check against. Hashlib is going to be used for cryptographic hash functions. String is going to be used for character sets. So for simplicity, in this demonstration, we're just going to be limiting passwords to lowercase letters for our password combinations. So itertools is going to be used for generating password combos, and then the time library we're going to use to track the execution time and compare how long it takes to crack each password in our examples based on the length and complexity. So running through the script's key functions, parse input is going to be used to handle command line arguments for the hash and the word list path. The hash is required to be specified. The word list is not. The default is going to be the rocku.txt word list, which is really common, really popular, contains over 14 million passwords. When you download it, it goes to user share word lists, generally speaking. Otherwise, you can specify any word list using its absolute path on your system. So we're going to return the hash and the word list from that function. The next function is identify hash algorithm. This simply is used to determine which hash it is based on the length of the hash that is specified. So for example, the SHA-512 hash, we know that that is a 512-bit hash, and hashes are expressed in hexadecimal. So since each hex character represents 4 bits, then we know that the length of the SHA-512 hash is going to be 512 divided by 4, which is 128. Likewise, with SHA-256 divided by 4, it's going to be 64 characters long. So based on the hash that we input and its length, it's going to identify the algorithm that was used to generate that hash. Check against word list is going to be the beginning of our password cracking process. This is just the dictionary attack. So it tries to find the password in a dictionary of common passwords. In our case, it's going to check the rocku.txt word list. So one thing to note is this right here, I wanted to just call out the fact that cryptographic functions work on bytes, not strings. So here we have to take the word, encode it into bytes, and then we hash it, and then we take the resulting hash bytes and convert those back into a readable string. And then we compare that string with our target hash that we specified in our command line argument. Finally, if we're able to match in the dictionary, amazing, we're done. That will happen very quickly. Otherwise, we're going to have to move on to brute forcing, which does not happen quickly, generally speaking. This is going to systematically try every possible combination of letters if the dictionary attack fails. So for demonstration purposes, like I said earlier, we're only going to be keeping it short and sweet and using lowercase letters exclusively. So that's 26 total letters, which isn't very many combinations compared to using lowercase and uppercase or using punctuation, and obviously using digits 0 through 9. We're also only going to be using password combinations between 4 and 7 characters long. So this cracking is going to take a while, and this is only going to be with 4 to 7 characters, lowercase only letters. So that should kind of illustrate to you how important it is to use a lot of characters and use a lot of random punctuation and don't use any dictionary words. So we're going to track how many passwords we attempt to crack before it's ultimately cracked as well. So then we're going to run the main execution. We're just going to be using a time counter to keep track of how long it takes the program to execute, and then we'll go ahead and compare the times based on password complexity. So different passwords that I'm going to be using today. I already specified or selected these passwords strategically. So the password that I'm typing in right now is a password that I know for a fact does not appear in the word list. So that's XYNHXK. So it's a complex password, a bunch of random characters. And this is going to be the hash that it generates. And it's 6 characters long. So the next one that I'm going to be doing is, the next password I'm going to be doing is going to be the exact same password with 1 fewer character. So I'm using Terminator, which is a terminal application that lets you split the window, which is nice to have. So I want to do the exact same thing, and I want to give one fewer character. So the password used here, XYNHXK. Let's try XYNHX. And we're using the SHA-512. So this, among all of our options in our script, is going to be the strongest hashing function we have, just for context. So I'm gonna just wait a second before I run that. As you see, this is still working. Apologies for this ugly terminal. And finally, I want to use a password that is also 6 characters, just like our first password, but which I know exists in our word list. So ZXCVBV is a 6-character password. It actually starts with a Z, so from a brute forcing perspective, if this wasn't in our word list, it should take longer than the X, because it's going through systematically and creating every possible password combination. So for example, this right here starts with an X and is 5 characters. So once all the 4-character sets are done, it's going to start with 5-character sets. So if this was A, it would obviously crack a lot faster than, starting with a Z. So here we're going to run this with the hash cracking tool. What we're going to see is this is going to be a password that appears in our word list. This does not appear in our word list, but is only 5 characters. So it's going to be brute forcing 5 characters. This is not appearing in our word list. It's 6 characters, so brute forcing 6 characters. So when we run the word list, again, it's 14 million passwords. It's going to be instantaneous, more or less. Let me start this. This will take, my guess is 20 seconds. Okay, there you go. So the password match was found in under a second via our word list. This should be finishing up momentarily. So this just illustrates how dangerous it is to use a commonly used password. This isn't even a commonly used password. It just happens to be in this file. This file, rocky.txt, this word list, this is a word list, like I said earlier, that is actually taken from actual password dumps and actual breaches. So these are commonly used passwords. So the length of your password is important, but if you're using a common password, if you're using I love you so much, or password 1234 exclamation point, winter 2025 exclamation point, something like that. Doesn't matter how many characters it is, it's going to get cracked instantaneously if it's in a word list. So the length really matters. As you can see, it took us almost no time to crack this one. We cycled through 11.4 million passwords. Here you see it's still going. So yeah, one thing I just wanted to touch on is the fact that this is only 26 total characters that we're testing with this brute forcing. So if you add in uppercase, you add in digits, you add in special characters, there's approximately 96 total characters. So if you used a password manager that just generated a strong password automatically, what you're going to see is that the amount of total possible combinations is just incomprehensibly high. If you use a 20-character password with 96 different combinations with each character, if you checked 1 billion passwords per second, it would take you more years than the entire universe has existed to try every possible password combination. So it makes it computationally infeasible to ever crack by brute force. So to wrap up, hopefully this ends before I finish speaking. This is just a simple example, but some enhancements to the script that we could make that could speed it up would be using a library in Python like multiprocessing. So that library lets you divide the workload across multiple CPU cores. We could also use Hashcat, which is another Python library that uses GPU acceleration for cracking instead of relying solely on the CPU. So that's the script. As you can see here, we just finished our cracking. So this took about 20 seconds. I think the output got muffled. I think it took about 21 seconds. I have it timed over here. This took about 21 seconds. This took 276 seconds. So 4.5 minutes versus 21 seconds. So it took about 13 to 14 times longer to crack this password again, passwords that are identical, just had one more character. Took 13 times longer to crack this password than this one. This one went through 11.4 million combinations. This went through about 297 million combinations. So I only used this as an example. If we had done 7 characters, it would have taken, I would guess, an hour and a half, 2 hours to crack the 7. So the amount of time that it takes to crack is just going to increase exponentially with every additional character that you add. So to wrap up, I hope this was helpful in demonstrating the importance of using strong passwords and using uncommon passwords. That's the script. It's located on my GitHub, which is at I am Chris Quinn, and I hope you found this helpful. Thanks.